March 14, 2025. Tesla Gigafactory Shanghai, 2:15 a.m. local time. Production line supervisor Chen Wei stares at a spreadsheet that renders Elon Musk's 20 million vehicle annual production target mathematically impossible. Not because of battery chemistry. Not because of semiconductor shortages. Because of copper. Each Tesla rolling off the line requires 183 pounds of copper, 83 kilograms of the same metal that powers electrical grids, data centers, and renewable energy infrastructure across the planet. The calculation is brutal in its simplicity. Tesla delivered 1.79 million vehicles in 2024. At 183 pounds per vehicle, that consumed 327,570 pounds of copper, 164 metric tons from Tesla alone. Now multiply that demand by Tesla's 20 million vehicle ambition, 3.66 million pounds of copper annually, or 1,830 metric tons, just for one company's electric vehicle production. The global copper mining industry produces 23 million metric tons annually. Tesla's full production scale would consume 8% of world copper output for vehicles that represent a fraction of global automotive production. Tesla's copper dependency isn't theoretical. It's wired into every component that makes an electric vehicle function. The electric motor contains copper windings that convert electrical energy to mechanical force. The battery pack uses copper foil as current collectors in lithium-ion cells. Power electronics, inverters, and converters depend on copper for efficient power management. The wiring harness threading through the vehicle contains copper cables for high-voltage power transmission. A conventional gasoline car uses 18 to 49 pounds of copper. Tesla uses 183 pounds, nearly 4 times the copper content of traditional vehicles. The constraint isn't Tesla's manufacturing capability. It's physics. Copper possesses electrical conductivity properties that have no viable substitute for high-performance electrical applications. Aluminum conducts electricity but requires larger wire gauges for equivalent performance, increasing weight and reducing efficiency. Silver conducts better than copper but costs $800 per kilogram versus copper's $9 per kilogram. For mass-market electric vehicles, copper is irreplaceable. Tesla's production trajectory collides with copper supply realities that mining companies have understood for decades but automotive executives are just beginning to comprehend. Global copper mine output is projected to grow by only 2.1% in 2025 to 23.4 million tons, up from 22.9 million tons in 2024. That modest growth assumes no disruptions at major mines. But disruptions are accelerating. Chile's Collahuasi and Los Bronx mines are experiencing production declines due to lower-grade ore and delayed infrastructure projects. Peru faces ongoing labor unrest at Las Bambas. Indonesia's Graberg mine continues recovering from extended disruptions. The geographic concentration of copper production creates additional systemic risk. Chile produces 23% of global copper output, primarily from world-class porphyry deposits in the Andes, including Escondida, the world's largest copper mine. Peru contributes another 10%. The Democratic Republic of Congo and China each supply 8%. Just 5 countries control 49% of global copper mining. Any political instability, labor strikes, or operational problems in these regions immediately constrains worldwide copper availability. Tesla's copper consumption per vehicle is actually conservative compared to other EV manufacturers. Some electric vehicles contain up to 200 pounds of copper, while electric buses require up to 814 pounds. But Tesla's scale amplifies the impact. If Tesla achieves Musk's stated goal of 20 million vehicles annually, the company would consume more copper than many countries produce. Chile's annual copper output is approximately 5.3 million metric tons. Tesla's copper demand at 20 million vehicles would equal 34% of Chile's total copper production. The automotive industry's broader electrification plans compound Tesla's copper requirements exponentially. California has committed to only selling new zero-emissions vehicles by 2035. The European Union plans to ban internal combustion engine sales by 2035. China, the world's largest automotive market, is pushing aggressive electric vehicle adoption targets. If global automotive production shifts toward electric vehicles, copper demand from the transportation sector alone could absorb a significant portion of total mining output. Current electric vehicle production represents only the beginning of copper demand acceleration. Global EV sales reached 14 million units in 2023. Industry projections suggest 50 million electric vehicles annually by 2030. At Tesla's 183 pounds of copper per vehicle, 50 million EVs would require 4.6 million metric tons of copper, 20% of current global mining production. That calculation excludes the copper required for charging infrastructure, electrical grid upgrades, data centers, renewable energy installations, and traditional industrial applications that continue growing simultaneously. The charging infrastructure supporting Tesla's vehicle sales creates additional copper demand that compounds the supply constraint. Each Tesla supercharger station contains substantial copper wiring for high-voltage power delivery. Tesla operates 7,702 supercharger stations globally as of September 2025. The company plans to expand to accommodate millions of additional vehicles. Each charging port requires copper cables, transformers, and electrical connections. A network of 5 million charging ports, projected as necessary within the next decade, would consume thousands of metric tons of copper beyond vehicle production requirements. Tesla's Gigafactory network reflects the company's attempt to vertically integrate manufacturing and reduce supply chain dependencies. But copper procurement cannot be solved through vertical integration. Copper mining requires geological deposits, mining expertise, environmental permits, and decades of development time. Tesla cannot mine copper the way it manufactures batteries. The company depends entirely on global mining companies and commodity markets for copper supply. The pricing implications of Tesla's copper dependency are already materializing. Copper prices increased 9% during 2024, reaching an annual average above previous year levels. Analysts attributed higher prices to expectations for reduced global copper supply concurrent with optimistic sentiment regarding world copper demand. Tesla's production ramp-up coincides with copper demand from artificial intelligence data centers, renewable energy installations, and global infrastructure modernization projects. Tesla's financial model assumes copper prices remain manageable relative to vehicle pricing. But copper represents a significant cost component that scales directly with production volume. At current copper prices of approximately $9,000 per metric ton, the copper content in each Tesla costs roughly $750. The geographic distribution of Tesla's production facilities reflects the company's awareness of copper supply vulnerabilities. Tesla's Shanghai Gigafactory produces vehicles primarily for Asian markets where copper supply chains are most accessible. The company's Texas and Berlin facilities serve regional markets to minimize transportation costs for both vehicles and raw materials. But geographic distribution cannot solve absolute copper scarcity. Tesla's competition for copper extends beyond automotive manufacturing. Data centers supporting artificial intelligence applications consume massive amounts of copper for power distribution and cooling systems. Renewable energy installations, solar panels, wind turbines, electrical grid connections require copper for electrical components. These applications compete directly with Tesla for the same copper supplies from the same mining companies. The timelines for expanding copper production cannot match Tesla's production growth ambitions. Developing a new copper mine requires 15 to 25 years from exploration through permitting to full production. Even expanding existing mines takes 5 to 10 years for significant capacity increases. Tesla's production targets assume copper availability that the mining industry cannot deliver within the required timeframe. Ore grades at existing copper mines are declining, making extraction more expensive and resource-intensive. Chile's average copper grades have declined by 30% according to the International Energy Agency. Lower ore grades mean mining companies must process more material to extract the same amount of copper, increasing costs and energy consumption while reducing productivity. This trend affects the entire global copper supply, not specific mines or regions. Tesla's recycling initiatives partially address copper scarcity but cannot solve the fundamental supply gap. Copper is infinitely recyclable without losing quality. Tesla's battery recycling facilities recover copper from end-of-life vehicles and battery packs. But recycling provides only 20% of current refined copper supply. New copper mining must supply the remaining 80%. As Tesla's production scales, recycled copper becomes a smaller percentage of total copper demand. The geopolitical implications of Tesla's copper dependency create additional supply vulnerabilities. China imports 60% of global copper ore and produces more than 45% of refined copper. Chinese companies control significant copper mining operations in Chile, Peru, and the Democratic Republic of Congo. Tesla's copper supply chains run through Chinese refineries regardless of where mining occurs. Any trade tensions or geopolitical conflicts affecting Chinese copper operations would directly impact Tesla's production capability. Tesla's Cybertruck, launched in limited production, illustrates the copper intensity of advanced electric vehicles. The Cybertruck's stainless steel construction requires additional electrical systems compared to conventional vehicle architectures. The vehicle's 800-volt electrical system, advanced computing capabilities, and integrated charging technology increase copper content beyond Tesla's standard vehicle platforms. If Tesla achieves projected Cybertruck production volumes, the copper demand per unit will exceed the company's current £183 average. The regulatory environment increasingly mandates electric vehicle adoption without addressing copper supply constraints. California's Advanced Clean Cars 2 regulation requires 35% of new vehicle sales to be zero-emission by 2026, increasing to 100% by 2035. European regulations impose similar requirements. These policies assume copper availability that mining industry executives privately acknowledge cannot be supplied at required volumes. Tesla's energy storage business competes with its automotive division for copper supplies. Tesla's Megapack utility-scale battery systems contain substantial copper content for electrical connections, power electronics, and cooling systems. Tesla deployed 31.4 GWh of energy storage in 2024. The company's energy storage growth targets require copper allocation decisions between automotive and stationary storage applications. Supply chain analysis reveals Tesla's vulnerability to copper mining disruptions thousands of miles from manufacturing facilities. The El Teniente mine in Chile, operated by state-owned Codelco, experienced extended disruptions affecting global copper supply. Kamoa-Kakula in the Democratic Republic of Congo faced operational challenges. Indonesia's Graberg mine, the world's largest copper and gold mine, has experienced recurring production problems. These disruptions directly affect copper availability for Tesla's manufacturing operations. Tesla's copper procurement strategy involves long-term supply agreements with mining companies and metal traders. But these agreements cannot create copper that doesn't exist. They can only secure Tesla's priority access to available copper supplies, potentially at the expense of other manufacturers. As electric vehicle production scales across multiple automotive companies, competition for copper supply agreements intensifies. The infrastructure supporting Tesla's manufacturing creates additional copper demand beyond vehicle production. Gigafactories require extensive electrical systems, manufacturing equipment, and facility operations that consume copper. Tesla's expansion to 20 million annual vehicles necessitates corresponding expansion of manufacturing infrastructure, multiplying copper requirements beyond per-vehicle calculations. Tesla's attempt to address copper scarcity through supply chain partnerships demonstrates the severity of the constraint. The company has explored direct investment in copper mining projects, partnerships with mining companies, and alternative supply arrangements. But these initiatives require years to materialize and cannot address immediate production scaling requirements. The Chinese electric vehicle market illustrates copper demand acceleration beyond Tesla's individual requirements. Chinese EV manufacturers including BYD, NIO, XPeng, and Li Auto are scaling production rapidly. BYD alone delivered 1.8 million electric vehicles in 2024, slightly exceeding Tesla's global deliveries. Each Chinese EV contains comparable copper content to Tesla vehicles. Combined Chinese EV production amplifies global copper demand far beyond Tesla's individual impact. Tesla's Model Y, the company's best-selling vehicle, represents the collision between mass-market EV adoption and copper supply constraints. The Model Y achieved 1.2 million global deliveries in 2024. At 183 pounds of copper per vehicle, Model Y production alone consumed 219,600 pounds of copper. Tesla's target of producing 2 million Model Y vehicles annually would require 366,000 pounds of copper just for this single model. The electrical grid infrastructure supporting Tesla vehicle charging creates a secondary copper demand that scales with vehicle sales. Each Tesla sold requires corresponding electrical grid capacity for home charging, workplace charging, and public charging infrastructure. Grid upgrades, transformer installations, and power distribution systems contain substantial copper components. This infrastructure copper demand multiplies Tesla's per-vehicle copper impact. Tesla's competitive positioning depends on copper availability that mining companies cannot guarantee. If copper becomes scarce or expensive, Tesla's production costs increase while vehicle performance may suffer. Copper substitutes, aluminum wiring, different motor designs, alternative battery technologies, compromise efficiency, range, or manufacturing cost. Tesla's technological advantages assume unlimited copper supply at predictable prices. The mathematical reality confronting Tesla's copper dependency is inescapable. Global copper mining produces 23 million metric tons annually. Tesla's 20 million vehicle target requires 1.83 million metric tons of copper, 8% of world production for one company. Add copper demand from competing EV manufacturers, charging infrastructure, data centers, renewable energy, and traditional industrial applications, and total demand exceeds mining supply by millions of metric tons. The timeline mismatch between Tesla's production scaling and copper supply expansion creates an inevitable collision. Tesla plans to reach 20 million annual vehicles by 2030. Copper mining projects required to support this demand would need to begin development today to achieve production by 2030. But those mining projects do and exist. The exploration, permitting, financing, and construction required cannot be completed within Tesla's timeline. Tesla's stock valuation assumes production growth that copper supply cannot support. The company's market capitalization reflects expectations of continuous vehicle sales increases. But if copper scarcity constrains Tesla's manufacturing capability, revenue growth becomes impossible regardless of market demand or production efficiency. The constraint is physical, not financial or technological. The reckoning is mathematical. Tesla's copper addiction requires more copper than the Earth's mining industry can provide at the scale and timeline required. Every Tesla vehicle needs 183 pounds of copper. Every additional Tesla produced competes with data centers, renewable energy installations, and other manufacturers for the same constrained copper supplies. Tesla faces a choice: scale production within copper supply constraints, or find alternatives that compromise the electrical performance that makes Tesla vehicles competitive. Physics and geology will determine the outcome. The copper exists in the ground, but extracting it requires time and investment that Tesla's production timeline cannot accommodate. The autopsy is complete. The diagnosis is clear. Tesla's 183-pound copper addiction per vehicle collides with mining industry realities that cannot be overcome through manufacturing efficiency or financial resources. When automotive ambition meets geological constraints, geology wins. The only question remaining is how Tesla adapts its growth trajectory to the physical availability of copper that powers every vehicle the company produces.